Howdy y'alls, it's the Diabolic V-Tutor, and we're going to be back with Trig, continue on the Trials of Trig, and we're moving on to a new property. It's going to be the angle sum, or angle difference identity property. It's going to be annoying, so let's get started on that one. Okay, we've covered a good amount of the basic trig situations leading up to, I guess, including Sokotoa, and that's basically it. Doing problem solving algebraic situations with x involved in the basic trig functions. And now we just have an additional fun property to deal with, and by fun I mean it's annoying. But it is what it is, and the unfortunate or fortunate situation, depending on how you look at it, is this property does show up again in that you need to use it to derive the subsequent properties, including the double angle property, the half angle whatever property, and then the angle sum situation. So this is pretty much the foundation. All right. So let's first just write this down. Of course. So we have the sine addition one. So if you have sine, why is this so thick? All right. So we have the sine. So if you have sine of angle number 1, we'll call this one angle alpha, and then plus angle beta. Then what we can do with this situation is we can expand it, and it expands into sine, cosine, cosine, sine. So sine of, this is the first argument from left to right, so it's going to be sine of alpha, and then times cosine of the second term of the argument, which is going to be beta, and then sine. We're gonna keep the same sign, so it's gonna be positive right here, and then we just alternate it into cosine argument first term, and then times sine of the second term of the argument, which is beta. All right. So that's the first one, the first angle slash difference identity property for the trig function sine, and then we have the cosine one. Cosine is going to be same arguments. We're going to have the alpha plus the beta. When you expand this out, it's going to be cosine of term number 1 of the argument, from left to right of course, times cosine term number 2 of the argument. And here's the goofy part, it's going to be minus. This seems to be a recurring motif when you're working with trig properties, unfortunately. And then sine alpha times sine beta. And then we have the funky one, tangent. And this is honestly the worst one. So we have sine of alpha plus beta yet again as the argument. Then that one is going to be tangent of the first one, and then plus tangent of the second one, all over 1, since this is plus, this is going to be minus tangent of the first one, and then times tangent of the second one. Have fun memorizing that junk. Let me just fix this up just a little bit. It's kind of bothering me how it's a low offset. Oh no, there's like a tiny little pixel there, isn't? Oh no, no. Okay, never mind. It's just a dirty monitor screen. Whoops. Okay, so here it is. Here are the 3 main properties, and then of course we have some variations of this one. And honestly, if you're required to memorize this, it's kind of awful. But here is the nice thing. You can use some mnemonics to try to remember this. And again, these ones are going to be the basis for the derivations of the other properties in this particular, for the rest of the trig section. Again, double angle, half angle, sum to product rules for this junk. It's just going to be ultimately derived from these from these two at least. All right. So sine, the way I like to remember is you sine, you keep the same sign. So this is the sine function, and the mnemonic that I like to use is if this is a plus, then that is a plus because you are keeping the same sign. And here's the thing though, if you had started with a minus, then you would continue with the minus. So if you had a plus between the two angles, then it's going to be plus because sine keeps the same sign. And then if you have a minus, then it will also be a minus between those two terms. When dealing with the cosine situation, cosine, I like the mnemonic I like to use for this one is is like company or cooperate or co-op, meaning together. So for this situation, the trig functions of the same types are kept together. So cosines, the cos are kept together, and then the sines are kept together. So that's the way I like to think about this one. But sine, whereas sine keeps the same signs, cosine does not keep the same signs. So if you start off with a plus, it ends up with a minus. If you start off with a minus, then you end up with a plus for the situation. So fun times, of course. So just to reiterate, cosine, you keep the two types of trig functions together. So the cosine is with the cosine. With the sine function, you have to keep the same signage. And hopefully that would be marginally useful. And then the tangent one, well, this is kind of a doozy to memorize, honestly. But if you recall, tangent is simply you could rephrase this as a ratio between two trig functions. So you could rephrase it as sine to cosine. So in a pinch, if you're asked to evaluate something and you can't for the life of you remember what the tangent expansion was for the angle sum, you could just use this one. Tangent is just simply the ratio between those two, and hopefully you memorize that one. Again, sine keeps the same sign, and then cosine one, you keep the two trig functions of the same types together, because co is like cooperate or company or coordinate. So same types. So that, again, that's in a pinch. If you don't know, if you didn't memorize this one in particular, then try to use this one. So that's why I don't consider this one to be super important. This is more important when you have to do trig proofs, and those are also kind of annoying, unfortunately. Okay, but anyway, so to help memorize this one, it's because the tangent function is the ratio between sine and cosine. The sine is on top, so we're going to keep the same sign. And then, of course, because as a cosine, you need to alternate it, and thus there's an alternation. Too bad, you're just going to memorize this as a sum, and then this one's a difference. However, if you start off with a subtraction difference between those two angles, then it would be a difference between the top two tangents, and then it will be a plus between those two. So those are the rules we're going to be working off of. So let's get started on some basic problems. I'm going to take this one and I'm going to shrink it so we can refer to it. Wait. Well, before I do that, I'm sorry. Let me put a... Okay, there you go. Whoops. That's going to be equal to, and I'm going to take this one and I'm going to move it over. Again, if you haven't memorized, in a pinch, you could always use the fact that it's a ratio between sine and cosine. So slightly less things to memorize, but it will cost you speed and maybe a proof. So we'll refer to that up there. Alright, so for the most part, we've been working with problems where we have very nice situations. If you recall, the perfect angles that we're dealing with are variations of pi over 6, variations of pi over 4, variations of pi over 3. These correspond to the special right triangles. You know, the 45, 45, 90 and their variants, and then the 30, 60, 90, and then the 30, 60, 90 for those ones. And then we have the interquadrant angles. We have those variations of that. And then we have just straight up interquadrant variations of those ones. So again, by variations, I just mean like you have like a number up here. So it could be like 5 pi over 6. It could be 11 pi over 6. It could be negative. It could be positive. This one, the variations, for example, would be 3 pi over 4. Could be 5 pi over 4. All the typical variations of those ones, etc., etc. So this one, the variation could be like negative pi. Variation could be 0. It could be positive 5 pi, for example. So I would consider those variations of this one. So for the most part, we've been dealing with stuff like this one. But now, of course, we're reaching more annoying terms, annoying arguments for our trig functions. So what do we mean by that? Well, here's a problem. Number one, we're dealing with sine function, and then the argument is going to be 5 pi over 12. Already, we can see that's different. So there it is. It's not our favorite variations of, for example, 5 pi over 6. This one, we have the tools to do it. But this one, prior to the properties listed minutes before having this, we wouldn't be able to do this problem. Unless you have like double angle formula. But again, double angle formula ultimately comes from one of these things right here. So here it is. So the question is, how do we evaluate this one? Well, where was this introduced in the first place? Because we have a single argument, and the argument consists of two terms: angle number 1 plus or minus angle number 2. So if alpha plus beta is a nasty argument, what shall we call this? Let's call it theta. So there are situations where we are asked to take the trig function of a particularly bad angle, but that bad angle isn't super bad because we can transform this one. We can break up that angle into two nice angles that we're familiar with. So for instance, if this theta isn't too great in the beginning, and then if upon further analysis, if you break it down, you might get like it's a pi over 2 plus a pi over 3. In this case, that would be, well, that's a bad example, but let me do another one. Pi over 4 plus pi over 3. And then this one, these two angles, we know how to work with that. So if we slam dunk the pi over 4 as an argument into the sine, we can do it. And then if we slam dunk that one into the cosine, we can do it, right? But if you sum up those two, that gets to the original angle that we saw that we couldn't really work with without this manipulation. So summing those two, we're going to get the 7 pi over 12. So that one is the bad angle. If we started with the 7 pi over 12, normally we wouldn't be able to do it. But with this one weird trick, we can turn it to situations where we can resolve it. Alright, so let me clear this real quick. Well, that's it for the Control Z. Alright, so here's back to this problem. So again, the situation is we can't deal with this 5 pi over 12 without some sort of manipulation to transform this one into a sum or a difference of angles that we are more familiar with. You know, the pi over 3, the pi's over 4s, the pi over 6s, or the pi over 2s, or the pi over 1s. So we want to usually transform this one into one of those situations, or their variants, right? So that's if the problem's nice, of course. If there are situations later on when we deal with this one, the argument, there's not much we can do with it. Wait, why did I delete it? Alright. So this is the particular problem. Let's just try to break this down as much as possible. So can we break down 5 pi over 12 into a sum of two nice situations? So thing number 1 and thing number 2, right? How do we break this down? Well, I guess in the sloppiest sense, we can just simply do 12. Try to imagine a number right there. It's kind of like a guesswork. And then if you assume plus, try to imagine a number up there as well that you can split the 5 into. Well, 5, we can split it up into 5 plus 0, which is not very useful because this is what we're starting with. So don't do that one. We can do 4 and 1. So if you split up 5 pi into 4 pi plus 1 pi, let's see what that looks like. If only I could delete things. All right. So if we split the 5 pi into 4 pi over 12 plus 1 pi over 12, this one becomes a nice situation. It becomes pi over 3, which, you know, it's one of those nice variants. But the pi over 12 is not a nice variance, so this one is not the optimal split. So rather than do 4 and 1, we can do 3 and 2. And that's going to be the very nice one, because 3 pi over 12 simplifies into pi over 4. And then the 2 pi over 12 simplifies into a nice pi over 6. And then these two are familiar faces. We've dealt with them before, so therefore let us transform this nasty argument into the sum of two nice arguments. So we're going to transform that into sine of pi over 4 plus pi over 6. And again, we're doing this because we now have a new property at our disposal. It's going to be the angle sum identity property for our trig functions. If this is a nice angle situation and this is a nice angle, we could expand it into a sum. So sine, you keep the same sign, but we don't keep the same trig types together. So it becomes sine, cosine, plus cosine, sine. So sine of the first argument, pi over 4, times cosine of the second term of the same argument, so pi over 6. Again, sine, keep the same sign. So it'll be plus. And then now we just do the old switcheroo. Cosine of the first term of the argument times sine term of the second term of the argument. So there's a whole switcheroo. You can use whatever mnemonic you wish to memorize this one. I just prefer to do it this way. Sine, cosine, cosine, sine. But you are very well entitled to change it into sine, cosine plus sine, cosine. It doesn't matter. But the important thing is as long as we are consistent with the property that we're using. So this is term number 1 of the argument, term number 1, term number 1, and then this is term number 2 of the argument. And this is here and there. Just to re-emphasize, this is a plus. Sign, keep the same sign, so it is plus. Alright, and now that we have the correct setup, now that we successfully split this one into two nice angles, this just becomes kind of a tedious follow through. So we just got to clean things up. So sine of pi over 4, just do a quick sketch. It's in quadrant 1 for the 45, 45, 90. It's a 1 to 1 to root 2 ratio. And sine just simply reports the ratio of opposite to hypotenuse. So I'm going to change it to root 2 over 2, rationalizing real quick. And this one is going to be pi over 6. That's also in quadrant 1. It's going to be the slim angle, 30 degrees. The ratio is going to be root 3 to 2, adjacent over hypotenuse for this one. This one I will also rationalize, so therefore, oh no, it's already rationalized. It says root 3 to 2. So the product is here, and then we're just going to copy paste the plus, and then we will reference the right triangles for these ones. So this is cosine pi over 4. We already have the sketch drawing. It's going to be same thing as this one. So plus root 2 over 2 times sine of pi over 6. That's opposite over hypotenuse. So a lot of this is making sure you reference the right things, of course. Organization is key for you chaotic brain people like me. We have this one. Evaluating that one, we have root times root, so we just get root 6 over 2 times 2 is 4. That one's pretty nice. It's just going to be root 2 over 4. And of course, we have same denominators, so we can simply summate the two numerators, but these are two different type of radicals, so they are uncombinable, so don't put root 8, for example. So we will leave it as a root 6 plus root 2 over 4. And that's probably the best we can do for this particular situation. Alright, so that's it for this particular problem. Again, just to recap, we have a nasty looking argument, but big hint. It has a denominator of 12. So that encourages us to split it up into two nice angles that we are familiar with, which is pi over 4 and pi over 6. And then using this new property, we can take this one and expand it into a situation that we can evaluate. And then you go through the tedious evaluations, simplifying to get to the final answer, and then we are good to go. So that is problem 1. And then you'll notice for the vast majority of these problems, the denominator is a very big clue about how you can split it up. So next problem, we have pi over 12. So already that's a prime candidate because we know that the factors of 12, 4, and 3, which are very familiar denominators for nice situations that we are accustomed to dealing with, right? So we could have a 4 in the bottom, we could have a 3 in the bottom, we could have a 6 on the bottom. So these problems, when designing these problems, I felt like there was very little room for creativity. At least making nice problems. Okay. So in this situation, pi over 12 is not a nice situation because pi over 12 is not a familiar angle, but we know because this is a design problem, we can probably manipulate the pi over 12 into a sum or difference of two nicer angles. So this is a small angle, so we're probably going to do a difference of angle number 1 and angle number 2. Alright, so we have a 12. We don't know what this is, so I'm just going to call this A. And then we have a 12 here, and then we don't know what this is. I'll call it B. So that one. So what are some nice situations? Well, there's a certain artificiality to these type of problems, and we just need to be able to simplify this one, right, in order to get it to a nice situation. So the A needs to be like a 2, or needs to be a 3, or needs to be a 6, or something where you can cancel out a factor of 12, because, you know, the factors of 12 are 2 times 2 times 3. So if you can cancel out a 6, you can cancel a 4, or you could cancel out a 3, then that's a nice potential option for A. So here's the thing, we want a 1 pi, so the difference between A and B is going to be exactly 1. So you can kind of see there are some nice options we can definitely put. We can put 3 for A, and we can pick 2 for B, because that will allow us to simplify this junk into pi over 4, and then this other option 2 will allow us to simplify with a 12 to produce pi over 6. And then these two are very nice situations, and we know how to evaluate those ones. So that's one potential option, one potential route we can go down, but you can also change it into a 4 for the A and then a 3 for the B, because 4 pi minus 3 pi gives us 1 pi as well. And of course, the 4 divided by 12 is simplifiable, and then the 3 divided by 12 is also simplifiable. So it becomes a pi over 3 minus a pi over 4. So this is the second route that we could potentially go down. And it is, honestly, it doesn't matter which one you choose, as long as you stay consistent. So again, this is pathway, this is route 2, and then the first route if we had chosen 3 and 2. So if you chose 3 and 2, then the first term of the argument would be pi over 4, and then the second term would be pi over 6. So let's just pick this one first, arbitrarily, and then we'll show that it doesn't matter which one. We'll select both in the end. So let us venture down a route 1 first. So we're splitting this singular pi over 12. We're going to split that into a difference between pi over 4 and pi over 6. This is a cosine expansion. We have a difference between angle number 1 and angle number 2. So therefore, cosine, you keep the trig functions together. So the cosine sticks with the cosine, and then the sine sticks with the sine. Okay, that's just the algorithm I use. Only sine keeps the same sign, so this is a minus, so we have to put a plus. This is going to be argument number 1, and then this is going to be argument number 2. So we just need to make sure both arguments, both terms, end up somewhere here and there, and then the blue one ends up here and there. So for this one, since it's cosine and cosine, it doesn't matter which order technically, but just to have some sort of order to this chaos, I'm just going to stick red one first and then blue one second. You know, I just think it makes it easier for me to keep track. And then the pi over 4 is quote-unquote first, so I'm going to put it right here. And the pi over 6 is second. Putting it right there. Okay, so that is using the expansion property. This one right here. Cosine keep the same trig functions together, keep the same trig functions together. You have to flip the sign because this is not the cosine one. I mean, this is not the sine expansion property. And from here on, it just becomes the standard situation we are familiar with. Cosine of pi over 4. That's in quadrant 1. I'm going to list all the ratios. It's going to be 1 to 1 to root 2. And this is going to be pi over 6. It's going to be the slim angle yet again. And that one is root 3 to 1 to 2 ratio. So those are our two reference triangles. Take that one and move it up here-ish. And now we just get to evaluating. So cosine is going to be adjacent over hypotenuse. I'm going to rationalize it right off the bat, times, and then this one right here. Referencing this triangle is going to be adjacent over hypotenuse. This is going to be plus. Sine pi over 4, that references this one. It's going to be the same ratio as that one, as this one. So also root 2 over 2. And then evaluating the last trig function, pi over 6. That's going to be the sine, so opposite over hypotenuse is 1/2. And I think this is the same answer as the first problem we've done. But that's okay. There's a relationship between sine and cosine, right? So simplifying this one becomes root 6 over 4. And that one becomes root 2 over 4. Again, these ones, we can't combine them, but the denominators are the same. So we just leave it as root 6 plus root 2. All over positive 4. And this is the answer for the second problem. And then we're good to go. And that was taking root 1, or root A. So let's take root B. What if we'd chosen this one instead, right? We should get the same answer, hopefully. So in this situation, we're going to start over yet again. So instead of splitting the pi over 6, instead of splitting the pi over 12 into this one, we're going to split it into this combo instead. So now we're evaluating cosine of pi over 3 minus pi over 4. What does that equal to? Well, cosine, you keep the trig functions together, so it's going to be cosine with the cosine. You don't keep the same sign, so it's a plus. And then cosine, you keep the trig functions together, so it's going to be sine and sine. That is argument, term number 1 of the argument. So put it first from left to right, put it first from left to right. And this is the second term of the argument, so pi over 4, and then pi over 4. So there we are. We're now referencing different reference triangles. Well, kind of, right? This is going to be pi over 4. This is the one we're already familiar with from the previous situation. So reference triangle there, and then the other one is now pi over 3. So it's going to be the wider angle, opening it up to the root 3 for the opposite, 1 for the adjacent. So those are the reference triangle. So what is cosine of pi over 3? It's going to be this one, 1 over 2. So it takes care of this one, and then cosine of pi over 4, 1 over root 2, aka root 2 over 2. So we're done with that one. And then now plus sine of pi over 3, referencing this one. That's going to be opposite over hypotenuse. And then sine of pi over 4, referencing this one, 1 over root 2, aka root 2 over 2. And as you see, it's going to be the exact same answer. It's just flipped in the ordering. So we have root 2 over 4 plus root 6 over 4. But I'm just going to rearrange it to put the greater term in the front and then the lesser term to the right. Same answer as expected. We're good to go. Yep. Alright, so not too bad. But again, we do have to memorize this junk right here. So that's always annoying. Next problem up, we have sine of 7 pi over, guess what it is? 7 pi over, yep, that's over 12. Can we get other ones? Well, I don't know. When I designed these problems, I just made like 12 problems and that was it. But I think these are the most interesting problem types. I think if it's like over 12, if it's over 24, then you can always simplify it. It just devolves back to a 7. It always devolves back to something over 12, honestly, in my opinion. Okay, so the same situation right here. We have kind of a not a nice denominator. It's 12. It's not the 2, 3, 4, or 6 that we're accustomed to. So, you know, just change this one. So what will it become? So we're going to call that one a pi plus b pi, both over 12 at the moment. So again, if this is a nicely designed problem, then the sum or difference between a and b has to be 7. And then you consider the factors of 12, or any sort of combination of 2 times 2 times 3. So we need a difference of 7. So this one is going to be, what? It's going to be a 12, and then if 12 minus 5, there's no way to get a 5 from these multiples, from those factors, so 12 and 5 aren't going to be the greatest. So let's go for a sum instead. You can kind of see 7 consists of a 3 plus a 4, so let's do it in that particular fashion. So we'll set this one equal to the 4, or 3, it doesn't matter. So 3 pi, because that's one of the factors of the 12. So if we put 3, then this one becomes simplifiable, which is perfect. And then, of course, if we pick the 4, because 4 is a factor of 12, 4 pi over 12 is also simplifiable. It's not a coincidence. It is by design of the problem, right? So does 3 pi over 12 plus 4 pi over 12 equal this one? Yes, because 3 plus 4 is indeed 12. So this one seems to be the optimal breakdown for the argument. And of course, we just simplify this one right off the bat. So divide top and bottom by 3, we get pi over 4. Divide top and bottom by 4, we get pi over 3. Familiar arguments, we love those, we'll take those. So we're dealing with the sine function, and it's going to be plus. So here we go, we have sine of term number 1, pi over 4, plus term number 2. And ordering doesn't matter because this is summation. If you add it, it doesn't matter which order you put it in. Okay, so we're dealing with the sine trig function, so sine keeps the same sign. So it's going to be the alternation of sine, cosine, cosine, sine. Sine keeps the same sign. We have argument number 1. I'm sorry, we have term number 1 of the argument, so it goes here and there. And then we have term number 2 of the argument, it goes here and there in a nice alternating fashion. So just copy paste, copy paste, copy paste, copy paste. Standard problem at this point. Just make sure you reference the right thing. You can definitely skip this work if you don't need it. I'm just going to show it just to be, what's the word? Words fail me at the moment. I forgot what it's called. just to be complete, yeah. So this one is the 45, 45, 90. So it's going to be this classic triangle. And this is pi over 3, opening up to the longer side. Okay. Sine of pi over 4 is root 2 over 2. Cosine pi over 3, 1/2. Cosine of pi over 4, same thing as before, root 2 over 2. And then sine of pi over 3, opposite over hypotenuse. It seems we keep getting the same answer, right? That's okay. So I'm just going to switch the order. That's root 6, and then this is going to be root 2. Common denominator is at 4, and then we're done with this problem. Kind of bland, right? We have these same situations over and over. That's okay. And the next problem up, we have sine 9 pi over 6. So what do we do in this situation? Well, recognize that this is actually 6. That's a variation of one of the nice situations. This is already a nice denominator. We already have the ability to resolve this situation, to evaluate the situation without having to bust out our angle, sum, or difference identity situation. So this is nice. There's no need to be extra. So let's evaluate this one using the way we already know how to do it. So again, denominator 6, this is a variation of pi over 6, probably, because this is just a 9, right? Well, let's see. So which quadrant do we end up in? So this is going to be quadrant 1. Nope. So 9 is past 6, so we're past halfway point. How much are we past? Well, we have 3 pi over 6 left over, which is half a circle. So this is actually an interquadrant angle, right? Yeah. So again, from here to here is going to be half circle, which is a full pi. So that's 6 pi over 6. So a spillover of 3 pi over 6 means it's halfways to full circle. So thus we are right here. 3 pi over 2. So interquadrant angle, this is going to be the downwards quote-unquote collapsed triangle where the opposite is equal magnitude with the hypotenuse. But since it's going downwards, it's going to be considered a quote-unquote negative opposite. So we have negative 1 over 1, which you could just jump straight to negative 1. So that should be the answer, right? So let's be a little extra. Let's actually apply the new property just to practice that one. But don't jump to the properties unless you really need to do it. So since we already have pi over 6, which is probably a nice situation, we could just evaluate it thusly. Alright, so that's the answer we're aiming for, or we're looking to verify, so let's independently use this one. So what can we split 9 pi into, right? So we have 9 pi over 6. We can hypothetically split it up into a plus b pi. And both of them are over 6. So how can we nicely split the 9? Well, we can do a difference, we can do a sum. I think the sum is easier to do because 9 can, right off the bat, see we split it into 6 and a 3. I guess that's kind of cheating because since we already talked about it right here, right? Because this is going to be half circle rotation. This is going to be the extra spillover. So, is it truly independent method verification? I don't know. Maybe, maybe not. But that's okay. So this one is going to simplify into just pi, and then this one simplifies into pi over 2. So that's what we're going to do. We're going to split this one, which you can see is simplifiable, right? This is 9 over 6. It's simplifiable. You can simplify into 3 pi over 2, which is exactly what we did before. Okay, but again, we're supposed to be, quote-unquote, using an independent verification. Kind of. So we have sine of argument pi plus pi over 2. Let's just use the expansion as practice again. So this is sine, so we keep the same sign, but the trig functions are mingled. So sine, cosine, cosine, sine, keeping the same sign. Argument number, term number 1 of the argument goes here and there, and then term number 2 of the argument goes there and there. So just reference and copy paste. There we go. So get to the evaluation. These are all interquadrant angles, so this one is going to be this, where we have the adjacent is equal magnitude with the hypotenuse, but because it's going in the left direction of the x-axis, it's -1. And this is the pi over 2. That's the interquadrant angle pointing quote-unquote upwards, collapsed triangle, where the opposite is equal magnitude to the hypotenuse. All right. Evaluating sign of this one. This is the, again, collapsed triangle. The opposite is essentially 0, so we have 0 for this evaluation. And funnily enough, this one is also 0, right? Because this one, for this collapsed triangle, there's quote-unquote no adjacent. So 0 times 0 plus, this is going to be cosine of pi. It's this one right here, where we have a quote-unquote negative adjacent. So it's -1 over +1, equal magnitudes of the adjacent and the hypotenuse. And then this one is this interquadrant angle, where the opposite is equal magnitude with the hypotenuse, but because this points upwards on the y-axis, it's +1. So times +1 over +1. And then when we evaluate that one, this is a 0, so ignore, and then this is going to be -1 times 1, -1. That's the answer, and thus we verified this one using a slightly different route. That's good practice, just practice expanding this jump. Alright, so finally we have a different answer than the 3 previous problems, right? Let me just cross a few things out. So, again, more of the story is make sure you don't mindlessly follow the algorithms. If there's no need for the algorithm, then don't do it. Unless you're looking to practice problems. Or practice newfound properties. But if you're on like a time test, please follow the directions. And if you could avoid using a property, then avoid using the property. Next up, we have tangent of pi over 12. This should be familiar, right? We've already technically done this type of situation, the pi over 12 situation, but we've done it with a different trig function. But again, this is just for practice. So in this situation, we can use the expansion for the tangent, but figure out what do we split this angle into, because it's over 12, which is not a quote-unquote exactly the same as a familiar situation. So we can probably split it up into a pi over 12 plus or minus b pi over 12. Well, the usual trick is a has to be a factor of this one, and then b has to be a factor of this one. Otherwise, there's no point to doing this split in the first place. So factors of 12, 2, 2, 3. Factors of 12, same thing, 2, 2, and 3. We want the sum or difference between a and b to be 1. And again, technically we've already done this. So 3 and 2 are good picks. So if we set a is equal to 3, that's a good pick. And then we set b is equal to 2, that's also a good pick. And we will do it as a difference, because 3 pi minus 2 pi gives us the desired 1 pi. So that is a good manipulation. And we will apply our trig function to that one, but we should probably simplify this junk. So pi over 4 minus pi over 3. Pi over 6, I mean. Alright, so practicing the trig one. Hopefully we've memorized it by now, but if you haven't, sine, or I mean tangent, we're going to keep the same sign because tangent is going to be the ratio of sine over cosine. So the sine convention follows the sine convention on the top. So thus, we're going to get tangent of term number 1, and then it's going to be, keep the same sign because the sign is on top, so minus tangent of the second term all over 1, and then since the cosine is on the bottom, you don't keep the same sign, so it'll be plus. And then since cos together, then we'll mishmash the sine and the cosine together via multiplication. Wait, what am I saying? It's going to be the tangent together. We're keeping the tangents as a product together. I don't know. I don't have a great mnemonic for this one, unfortunately. But it should be this one. And then again, argument number 1, just copy paste. And then the term number 2 of the argument, just put it right there. Put that one right there. Alright, there we go. And just to make sure I'm not just making things up, here it is again. We have, if it's a sum, then it's going to be a sum of the tangents. And then if it's a sum, it's going to be a difference between 1 and the 2 tangent products. Yeah. So, there we go. So this one should be correct, and thus get to evaluating by sketching out the reference triangles. This one hopefully is super familiar. 5 or 6. As you do more and more tangent problems, I mean trig function problems, you're going to get so used to these ones right here. Alright, so tangent is just opposite over adjacent, so 1 over 1, and then tangent of this one is also opposite over adjacent, so it's going to be root 3 over 3 by rationalizing the denominator. Again, just skipping the 1 over root 3 step, skipping straight to this one. And all this is just going to be copy paste. We already know what tangent of pi over 4 is. It's 1 times what? Familiar face. It's that one. Alright, so at this point it just becomes simplification. It's actually kind of gross, isn't it? But, well, we'll do our best. So 1 minus root 3 over 3, and then the bottom one is going to be 1 plus root 3 over 3. Not the nicest looking situation, but leaving it like this, you will probably be deducted points. So let me let me move things over. Okay, so again, while technically correct, we should change this one because we have fractions within fractions. So we just need to clear the fractions. This is a 3 in the denominator, so we will simply multiply top by 3 and bottom by 3. So this is 1 equivalence. So it's a perfectly legal math manipulation move. So 3 distributed to the top 2 terms, we're going to get 3 minus root 3. And then 3 distributed to the bottom terms, we're going to get 3 plus root 3. So this is also technically correct. If your teacher requires you to go farther, then you need to rationalize this denominator. That one requires conjugates. Some teachers are okay with this as an answer, but I'm just going to go all the way, just in case. So we have to multiply by the conjugate. So multiply the top by 3 minus root 3. 3 minus root 3. And we're picking this one as a conjugate because it's going to create the difference of 2 squares scenario, where this one times this one gets you 9. And then this positive times negative gives us negative, and then root 3 times root 3 gives us just 3, and then the 2 middle terms are equal magnitude, opposite signs, so they will cancel. So that's how we clear the irrational term in the bottom. But then the top one becomes a mess, in my opinion. So 3 times 3 is 9. Nice. And then we have minus 3 rad 3 and another minus 3 rad 3. So minus 6 root 3. And then negative times negative gives us positive. Root 3 times root 3 gives us 3. So final cleanup step. 9 plus 3 is 12. 12 minus root 6. I'm sorry, 6 root 3 all over 6. Just kidding, not the final simplification. Terms on top and terms on the bottom are divisible by 6. So final answer, 6 plus root 3 over 1. And that should be it. I hope that's correct. Alright. So that is using the tangent expansion for a difference of 2 angles for this particular problem. So again, pi over 12 is not a nice situation right off the bat. So we split the pi over 12 into 2 nice terms we're familiar with. Once we have those nice familiar angles, we can use a property to expand the tangent into this nastiness. Using the reference triangle, we're going to evaluate each of those terms and factors. And the rest of this is just algebraic cleanup and manipulations. And hopefully this is the right answer. But to independently, as independent as possible, right? We're going to try to verify 6 plus root 3. So let us use a different strategy for this one. So tangent of pi over 12, again, in the weird case, or rather in the unfortunate case that you forget this particular property, you can always resort to the other property. Tangent is just a ratio between sine to cosine. So it's going to be a bit more work. So it's nicer if you do memorize this root, if you memorize this particular expansion. But again, this is talking about worst case scenario, you don't remember the expansion for the tangent. You could at least use this particular ratio. And this ratio is useful for other problems, like maybe even calculus. Alright, so the pi over 12 is, again, it's not a quote-unquote nice angle right off the bat. So we can split it up into a pi over 12 minus b pi over 12. Let's use slightly different numbers this time. So instead of picking 3 for A and 2 for B, we can pick 4 for A and 3 for B. Where did these come from? Came from the factorizing of 12. Because this type of problem is very, very, very artificial. And as a problem maker, you want to make the numbers nice for the students doing these problems, so, you know, you kind of cheese the problem a little bit. So 4 and a 3, the difference of which is 1. So that's going to be the breakup that we're doing. So 4 pi over 12 simplifies into pi over 3, and then 3 pi over 12 simplifies into pi over 4. But here's the thing, we're dealing with this nastiness, so we have to do the top situation, we have to do the bottom situation. So pi over 3 minus pi over 4. We're very familiar with those at this point. Alright, so sine expansion, sine, cosine, cosine, sine. Sine, keep the same sign. So that is going to be term number 1. And term number 2 of the argument. So here we go with the reference and copy paste. So pi over 3. Wait, I said sine, cosine, cosine, sine, but I wrote it as sine, cosine, sine, cosine. Whoops. So let's follow through. Ooh. I'm sorry, I just gotta beautify this real quick. Okay. There we go. So this is pi over 3 for the first term, so pi over 3 here, and then the second term is pi over 4. Pi over 4 here, and pi over 4 there. So that's the expansion on the top. And then for the denominator expansion, it's a minus. You only keep sign for the same. We only keep the same sign if it's a sign one. So since we have a minus there, then this one's going to be not a minus, but a plus. But then cosine keeps the two trig functions together. So it's going to be cosine, cosine. Whoops. And sine, sine. So I like to think about it, since this is the cosine function, I'm going to put the cosines first. Yeah. So term number 1, term number 1, and then term number 2, term number 2. And thankfully we could just copy paste those straight down. And that slightly expedites the situation. So that's the usefulness in keeping same conventions when you're memorizing your properties. So that's what we have. And then again, we're referencing the very nice situations. That's going to be pi over 3 in quadrant 1. So root 3 to 1 to 2. And then the pi over 4, quadrant 1, it's 1 to 1 to root 2. So kind of messy, but again, this is a kind of a last-ditch effort. Last resort if you don't have the tangent expansion memorized. So this is sine of pi over 3. Opposite is root 3 over 2. And this is cosine, which is going to be 1 over root 2. This one references this one. It's going to be 1/2. This one references that one, so root 2 over 2. So it's going to be the same ratios echoed over and over again. So this one is the same as this one. Right there. Cosine is just cosine is just going to be equivalent to that one, so you could kind of copy paste. This one is the same as that one, so that one. And then lastly, this is the same as this one. So unfortunately, things are getting rather cluttered. Let me try to move things around. That's the best I can do. Alright, so that is going to be equal to root 6 minus root 2 all over common denominator of 4, and the bottom one's going to be something very similar. It's going to be root 6 plus root 2 all over 4. Since the 4 is in a fraction and this 4 is in a fraction, we can just cancel, thereby getting root 6 minus root 2 over root 6 plus root 2. And that feels a little distinct from this one, right? But again, or rather, right off the bat, this one looks a little different from that one, right? But we just need to do a little bit of manipulations so that we can change this one into something that matches that answer. So, a little bit of manipulation. We have root 6 minus root 2. Over root 6 plus root 2. So if we rationalize it, it should change into that particular situation. So let us see. So the players are going to be root 6 with the root 2. Since this is a plus, we want a difference of 2 square scenario, so this is going to be a minus. Multiplication. Alright, so the two middle terms, the products of the two, those two products will cancel out, so we don't need to worry about that. We have to worry about 6 times root 6 times root 6 gives us a clean 6, and then the root 2 times root 2 gives us 2, but then the signage is going to be minus. Okay. And as for the top situation, so much space, so much work. Alright, so we have this one times this one. It's just going to be, so this is a classic binomial expansion situation. In fact, it's the perfect binomial situation, right? It's going to be root 6 minus root 2 squared. So we can follow our favorite algorithm if you wish. So that one squared is just going to be 6, and then this one times that one times 2. So thus, minus 2 times root 12. And this one is simplifiable. Wonderful. And this one squared is just going to be positive 2. So hopefully, this one equals this one. Let us see. So we have 6 plus 2, which is 8. And then we have a minus 2 root 12. Well, 12 one is 4 times 3, right? And then 4 is a perfect square, which is square root of 4 is going to be 2. 2 times 2 is 4. With a root 3 left over, and then we have a 6 minus 2, which is a 4. So on cleanup step, ooh, this is a different answer. That's interesting. So one of those is a mistake. No, that's okay. So we have 8. We have 8 minus 4 root 3 all over 4. Each of those terms is divisible by 4. 8 divided by 4 is 2. And then 4 divided by 4 is 1. So that is pretty distinct from that one. So, interesting. One of these answers is wrong, or both of them are wrong, right? Because they both can't be right. So, which one is correct? Well, it's honestly kind of a nightmare to work through. There's so much work to slog through. So let me see. Is the tangent root correct, or is the sine cosine root correct? So let me go back to the tangent function real quick. So in this particular situation, the pi over 12, we split it into these two. Is that correct? Yeah, this is correct. Split. Is this correct simplification? Yes. Yes, that's also correct. Okay, and then yes. Okay. And then checking for these ones. Is tangent pi over 4 1? Yes. Is tangent pi over 6 this one? Yes. Opposite over adjacent. So that should be correct. Okay, and then those two numbers are going to be copy pasted in the bottom like so. So that should be good. And then checking here. Oh, okay. When I did multiplication by the... No, this is the simplification. This one is that one. And then this one is this one. Yes, okay. So when dealing with this one, is the manipulation correct? 3 distributes to these two. Yes. 3 distributes to those two. Oh, this is the conjugate. This one is to this one. Yes. And then 1 times 3. Yes. So we get this one, and then we need to rationalize it, multiplying top and bottom by the conjugate. 3 times 3 is indeed 9. Root 3 times root 3 is indeed 3. Yes. So that should be correct. Interesting. Okay. And what else is there? That is correct. This is 3 root 3 plus 3 root 3. Yes. And then 9 plus 3 is 12. Yep. This one is, yes, that's correct. 9 minus 3 is 6. Yes. This one should be correct. It's supposed to be 12 divided by 6 is 2. And then 6 divided by 6 is 1. Huh. Wait a minute. Oh, I don't know how this answer was interesting. Where did this one come from? Because it seems like it is consistent. So, okay. So going on the tangent path, right? We get to this final result. And that should be correct. Well, I guess maybe I just botched at the math. Oh, I did 12 divided by 6 is 6. That's... I don't know why I put 6. Okay, so both methods are consistent. I don't know. I just failed the simple division. So I did 12 divided by 6 gives us 6, but that's incorrect. So this one... 12 divided by 6 is a 2, not a 6. Okay, so once this division is corrected for, then both methods result in this. Wait, this is a plus. Because this is a minus. Okay, I don't know how I flipped the signs. This is a minus right here, so it's supposed to be a minus. That's a really bad mishap. Okay, so keeping the signage here is the signage there, so this answer is now consistent with the other method. Okay, so both methods are in agreement. So it's not a failure of the method, it's a failure of my division and copy pasting the same sign. So that's on me. So 2 minus root 3, 2 minus root 3 is correct. That's a lot of work. Look at all that. And we shall move on to the next problem. It's going to be cosine of 5 pi over 12. Alright, it's a 12, so we need to change it. We need to split this up, probably, right? So what can we change it into? This one splits into a hypothetical 8 pi over 12. This one should be simplifiable. And then plus or minus b pi over 12. Again, this one should also be simplifiable. So how do we split up a 5? Well, you can kind of see it already, right? 3 plus 2. Why 3 plus 2? Because if a is 3, this is simplifiable. And if b is 2, that is also simplifiable. 4 and 1 is not good because this one is simplifiable, but then 1 doesn't simplify with the 12. So, not as useful. Can we potentially do other splits? Yes, we can. We can do, if you really want to be a little extra, you can. You certainly can. We can have a 9 up there, and we can have a 4 right there, and we can do a subtraction between those two. This is a little extra, like I said. But it's definitely possible because 9 minus 4 gives us the 5, and then 9 is simplifiable over 12, and then the 4 over 12 is also simplifiable. So let's be a little fancy this time. 9 minus 4. Again, we could have done the other route. If this is going to be 5, we could split it into a 3 here and then a 2 there. But we already did that. So just for extra bonus points, I guess, we have a 9 and we'll do a 4. Thereby that one simplifies into divisible by 3, divisible by 3, so 3 pi over 4. And then this one is pi over 3. So we're doing the 9 minus the 4, so it's going to be minus between those two inside the cosine trig function. So hopefully things end up a little more interesting than before, but if you can keep things in quadrant 1, you know, why not? It's going to make the numbers a lot nicer. But let's not lull ourselves into using the same things over and over again. So here we go. Sketch that one out. That's going to be in quadrant 2 for the reference triangle. 3 pi over 4. And the ratio is 1, negative 1 to root 2. This one's the classic pi over 3. We already know that multiple times a day. Root 3, 1, and 2. Alright, cosine function. That's the cosine expansion, so keep the trig functions of the same types together. So it's cosine, cosine. This is not sine, so don't keep the same sign, so it's plus. Keep the trig functions together, sine and sine. Arguments, we have term number 1, so it goes here and there. And then we have term number 2, goes here and there. So that's the setup. All we have to do is put the players where they belong. So 3 pi over 4. And 3 pi over 4. Pi over 3. So don't do this mistake. Don't put negative pi over 3 because the signage thing is part of the algorithm right there. That one dictates the sign between. So don't put it again right there. So just pi over 3. And that should be the expansion, and we should be good to go. Now let's just reference the right reference triangles. So let me move things over right here. Oh, that's small. There's some. Hold on. Yeah, all right. So 2 reference triangles are right there for our reference. So cosine of this one is adjacent over hypotenuse. So it's going to be negative root 2 over 2. Cosine of pi over 3, a familiar face. Sine of 3 pi over 4, opposite over hypotenuse. Sine of that one, opposite over hypotenuse. Familiar numbers, yet again. It's to be expected. Common denominator. Rearranging the terms. No need to rationalize or do anything like that, and we're pretty much done with this particular problem. There it is. And just for some more bonus points, let's just go with the first way. What if we kept the original numbers, right? So we'll pick a different starting position. So we're going to split this again into the 3 pi plus the 2 pi over to 12. Thereby getting cosine of 3 pi over 12, which is going to be pi over 4. And then 2 pi over 12 is going to be pi over 6. So let's just speed run this just a little bit. We have this one, so it's going to be cosine, cosine, sine, sine. Trig functions together. Don't keep the same sign. That's the first one, pi over 4, and then pi over 4. That's the second one, pi over 6, and pi over 6. My writing is getting worse and worse. Alright, so cosine of this one is going to be root 2 over 2. Cosine of that one is going to be root 3 over 2. Sine of that one is a very familiar root 2 over 2. And the sine of that one is 1 over 2. And yep, they are in agreement. So, good to go. So as you see, if you're very familiar with these numbers or very familiar with these special right triangles, or if you are very familiar with the unit circle, you can trudge through these problems a lot faster. This is showing not the full work. And now we have a maybe more interesting problem. Sine of 19 pi over 12. Again, the problems, they're going to be mostly 12 for the denominator. Not super creative. Alright, well, we got to split the 19, or... Yeah, we just got to split the 19, because 12 is not a familiar one right off the bat. We need a 3, we need a 4, or a 6, or a 1, or a 2. Alright. So hypothetically, a pi over 12 plus b pi over 12. A plus or minus, but for the most part, since this is bigger than 12, it's probably easier just to consider this as a sum of 2 rather than subtraction between 2. So how can we split the 19 into something divisible each by 12, right? Well, factors of 12, 2 times 3, and just play around with the factors in your head, right? So we can get a 12 here, and then we need a 7. Is that possible? Yeah. Wait, no, it's not. 2, 2, and 3. There's no way to get a 7, so this is probably not the right way to go. Let's keep going a little further. What do we have? This could be a 4. If that's a 4, this has to be a 15. Is that going to be possible? Well, okay. So now we see a little more interesting dynamics of the situation, right? Because 19 is going to be bigger than 12, so there are more factors that we can consider. And we're no longer just stuck with just having these ones right here, because again, these ones work a lot better. This whole thought process works a lot better when this number is small in comparison to the 12. So now we have additional things to play with. So here, this is what I mean. So 15 is actually a pretty good one, because if you have 15, the 15 isn't perfectly divisible by this, but parts of 15 are divisible by this one. So here's what I mean. If we have 15 pi over 12, this one is going to be simplifiable into 5 pi over 4. And this is a familiar variation of what we like. And 15 plus what equals 19? It's going to be 4. 4. And that's going to be a very nice breakdown right here. So we have this one, which simplifies into pi over 3. This one, which simplifies into 5 pi over 4. This is nicely, we can evaluate that one inside trig functions without the aid of a calculator, and we could evaluate this one as well. So this is going to be the good, probably the simplest breakdown of the situation. So I kind of glossed over it, right? So this is 19, like considering the factors of 12. We just need the top number to be divisible to cancel out with one of the factors, at least one of the factors of 12. So we could potentially cancel at one of the 2's, or the 3, or both the 2's, or a 2 and the 3. So as long as the number you're considering on the top is divisible somehow by some combo of the factors. It's going to make more sense as we do more problems, as usual. I don't know if that was super clear, but that's how I would approach the problem. Alright. So we are splitting that into a sum between pi over 3 and 5 pi over 4. Because this one is a nice situation, because 5 is 1 more than 4. 3 pi over 4 would also be a nice variation. Or something like 7 pi over 4 would be a nice situation, or even 3 pi over 4. So that's why it's nice if you memorize the unit circle, but you don't have to. Okay, so just to make sure this is correct, this is cross multiplication. 15 plus 4 takes us back to the 19, yes. So let's just use our expansion property. Sine, this is going to be sine, cosine, cosine, sine. Keep the same sign, or sine. Sine, cosine, cosine, sine. Plus, plus. Term number 1. Term number 2. And here we go. Copy, paste. Right there and right there. And then 5 pi over 4. Here and here. And sketching out the reference triangles, of course, this is just standard quadrant 1 situation. Root 3 to 1 to 2. And then this one is the quadrant. This is greater than, 5 is greater than 4. So that's spillage into third quadrant. So we're looking at the 45, 45, 90 in quadrant 3. Like so. Negative adjacent, negative hypotenuse, I'm sorry, negative opposite ratios. So the correct reference triangles have been sketched out. Now let's just apply the functions, trig functions. So signage of that one is root 2 over root 3 over 2. Cosine is just going to be times. Now here's a potential for error. Don't put minus root 2 over 2 because it's supposed to be times. So to avoid that, I'm going to treat this one as a parenthetical because parentheticals make things so much clearer. So parenthetical, this one, which is negative root 2 over 2. Plus, plus. Then, of course, cosine of pi over 3, 1 over 2. Signage of that one is going to get us a negative situation, so I'm going to put parenthetical real quick. Opposite over hypotenuse. Now it's just the opportunity for cleanup. We're going to get a negative root 6. This is going to be a negative root 2. Common denominator of 4. And we are done with this particular problem. And that's it. Nothing too exciting. Let's just practice some more of these situations. So we're going to basically be doing like 1, 2, 3, 4, 5, 6 more problems of this introductory type, and then we're going to move on to slightly more complicated problems. This is going forwards, and then we're going to go backwards as well. Alright, so here we go. So we have a sine of 5 pi over 4. Recognize that we don't really need to use the expansion for the situation because this is a familiar denominator of 4. So this is a 45, 45, 90. It has a 5 on the top, so that's perfect. In fact, we already saw this angle in the previous problem, right? This is going to be 4 pi over 4 if we have a spillover of pi over 4. So we are in quadrant 3. So this is already doable. Negative 1 to negative 1 to root 2. So signage of that is going to be opposite over hypotenuse. So we're done with the problem, but just for practice, let's just use the new identity we've learned, and we'll use this one as checking the answer. So how can we split that up? That will split up into some sort of a pi over 4 and plus or minus b pi over 4. And we just need a and b to be nice numbers to be divisible by 4 each, usually, or maybe not both of them. So we're going to set a is equal to 4 because 4 divided by 4 is a nice situation, and then thus we have to set b is equal to 1 because 1 over 4, it's not divisible, but it is a nice pi over 4 scenario. So this is a very simple breakdown, and we'll keep it like this one. So this one simplifies into just pi, and we're picking the addition, so this is going to be plus, this is a singular pi over 4. So thus we will break up the 5 pi over 4 into pi plus pi over 4. And then of course using the sign expansion, it's sine, so we keep the same sign but don't keep the two trig functions together, so it's going to be sine, cosine, cosine, sine. We have term number 1 and term number 2. Copy paste, and copy paste, copy paste. Interquadrant angles, of course, is going to be negative 1 adjacent. So this one, for the collapsed triangle, quote unquote, there's no opposite. So it's 0 times, this one is not going to be 0. Well, it doesn't matter, because 0 times discrete value equals 0. Alright, so cosine of pi, that's a negative direction for the x-axis. So -1 for this evaluation. And then for that one, well, hopefully we still remember that one. 1 over root 2. So evaluating that junk, we're going to get negative root 2 over 2, which is consistent with the first answer. And thus we're good to go. Again, this is just practicing the expansion. We didn't have to do it because it's already a nice situation. You getting tired of seeing the same numbers? That's okay. Hopefully, we'll ingrain these values, right? At least until the class is over. So we're dealing with cosine of negative 19 pi over 12. This is a same situation as 2 problems back, 19 pi over 12, but there's a negative sign. It doesn't make much of a difference, honestly. So the question is, standard, how do we break this up? Well, the -1, it may or may not confound things. I don't think it's going to be a big deal. But fun property. Okay, so if you don't want to learn this property at this moment, you can just ignore what I'm about to say. But cosine is an even function because of symmetry analysis of the graph. This is a whole nother topic. I'm not going to cover it today, but just as a reference for those of you who have potentially learned it, cosine is an even function, so thus you have a negative argument. You can transform into the positive argument, like so. And then you can evaluate this one like 2 problems ago. But let's ignore that for a moment. So let's say we don't have that at our disposal. So how do we break up this negative 19 pi? Well, same strats as before. Consider 8 pi over 12 plus or minus some sort of b pi over 12. And we just need to split the 19 very well. I think the last numbers we chose, the numbers from before, I don't remember which number we chose anymore. Oh, I think we chose 7. Yeah, no, we didn't. Let's just pick new numbers. We have a 5 and then we have a 14. So, oh, I think I remember now. It was a 15 and a 4, yeah. Because magnitude 15 plus magnitude 4 gives us magnitude 19. But we need a negative in front, so we can just put a negative here and a negative there. What needs to happen between negative 15 and negative 4? We need to summate those two to get negative 19 pi. There we go. That's the difference. So this one is going to be negative 15 pi over 12, which simplifies top and bottom divisible by 3. So negative 5 pi over 4. And then second term is negative 4 over 12. Negative 4 pi over 12. And that one we can simplify into negative pi over 3. And again, it's a sum between those two. So this whole thing will be term number 1, and this whole thing with the signage will be term number 2. And this is a sum between those two negative angles. So keep track of that. So we're going to expand this one into that one. So this whole negative term will be term number 1 plus term number 2. The spacing looks kind of weird, but again, this is going to be term number 1 with the negative, and then this is term number 2. And now it's just standard problem. Cosine, keep the two trig functions together. So cosine, cosine. Only sine keeps the same sign. Copy paste into here and there. And then that one goes into here and there with the signages. I didn't leave enough room. Okay, and now we just need to do a rough sketch of the reference triangles. This is now moving clockwise fashion. This is 1 greater than 4, so it's spill over into quadrant 2. So that is negative 5 pi over 12, negative 5 pi over 4. So negative 1 to positive 1 to root 2 for the ratios. And this other one is just going to be clockwise, big angle, opening up to the root 3. But since this is going down y-axis, it's negative root 3. Ratio is 1 to negative root 3 to 2. There we go. Now that we have the correct reference angles, let's just evaluate these. So cosine of this one is just going to be negative root 2 over 2. Inside the parenthetical to keep things safe, and then cosine of this one is 1 over 2. Minus opposite over hypotenuse. Sine of that one goes back to this one. We have negative opposite over 2. Okay, cleanup step. We know we have a common denominator of 4. This is just going to be negative root 2. And this is going to be positive root 6. So positive root 6, I'll put that on the left first, and then minus root 2. And that's it. Very familiar faces, root 6 and root 2, and then the 4 in the bottom. Wonderful. But we should be done with this particular problem. Again, quite a bit of work. If you're showing all your work, if you are required to show all your work. But sometimes, depending on teacher. DOT, depending on teacher. I'm actually going to skip over this next problem, which is tangent of... Oh, you know what? No. Let me not skip over it. I'm just going to do practice. So if you felt like you had enough, as a VOD watcher, you just skip over to another problem. So we have tangent of 5 pi over 12. Five pi over 12. Well, we're dealing with a tangent, so we can split this up. We're already familiar. 5 splits into 3 and 2, which is going to be pretty easy to deal with. For the split. There it is. But can we be a little extra? Can we do a subtraction situation? Yes, we can. So rather than do the easier situation, let's just practice seeing other numbers. So we have a 9 minus a 4, which is also nice. Because if we consider this as 9 pi over 12, that's simplifiable. And then minus 4 pi over 12. This is a nice situation. But we've also already worked with these numbers. So is there another situation we could potentially do, right? Well, what else is nice? 12 minus a 7. No, 7 is not a nice number because 7 has no common factors with 12, aside from 1. So not very useful for that one. We have a 16 and minus a 1. No, that's also not very nice. We have an 18 minus a 3. Okay, that one's pretty nice. So we desire a 5 pi on the top, which is... Well, what am I saying? This is 15. That's not quite what we want. That's only a 5, not a 15. Well, if I'd redesigned the problem as 15 pi over 12, then this one would be a very nice split. But we don't have this one, so too bad. You know what? Let's do it like that. instead of doing 18, why not just do 8 and 5, right? Because, oh, no. 5 is not divisible by 12, so that's not a very good situation either. Okay, so maybe we can do, oh, I know, 15 pi on top of the first term, and then 10 pi on top of the second term. Yeah, there you go. So this is a unique number combo we haven't tried quite yet. But again, you could always stick with the nicer numbers. There's no need to be extra. So for this particular setup, it's just being a little extra. So we have 12 pi over 12, and then we have 10 pi over 12. We're finding the difference between those two because 15 pi minus 10 pi gives us 5 pi. So again, you don't have to go down this route. So if you're practicing this from the VOD, just pick the easier ones and just see if our answers are independently verified. Okay. So this one is going to simplify into what? Divide by 3, divide by 3. 5 pi over 4. And then this one simplifies into divide by 2, divide by 2. So 5 pi over 6. Okay. So that's the situation we're dealing with. And what's the expansion, right? This is a tangent one, so tangent sine over cosine. So we keep the same signage. The minus is going to be on top, but then we have to flip the sign for the bottom portion. So it becomes tangent of term number 1. So sine is the top for the tangent ratio. It's going to be minus, keeping the same sign on the top. Tangent of the second term. Don't put the negative, because the negative here goes there. So this is just this one. All over. And then we have, oh, why am I circling that? We have a, again, this is a little bit of memorization, so 1 minus, but this is minus already. This is cosine on the bottom, so you have to change the sign. So it's going to be plus the product of those two. Doesn't matter which order you go, but try to have some sort of semblance of order. So I like to put this one first to stay consistent. Alright, so that should be the setup. Again, the minus is here, the minus goes on top, and then the minus is on top, so the plus goes on the bottom. Alright. And let's make sure we reference the right reference triangles. This one is going to be 45, 45, 90 in quadrant 3. So -1 to -1 to root 2 ratio. That one, and this is going to be 5 pi over 6. 5 is less than 6, so we are stuck in quadrant 2 with the slim angle. And the ratio for that is a positive 1 opposite to negative left of the x-axis, negative root 3 to positive 2 for the hypotenuse. So let's evaluate each of those. So this one is this one. -1 over -1 is positive 1. Minus minus. We have tangent of this one. What is that? That's opposite over adjacent. So here's how I like to do it. Keep the negative sign. Do the negative sign first. And then opposite over adjacent. So that's that. This is a 1 plus. We technically already have these evaluated. This one is already evaluated. This is why I like parentheticals. So if you simplify this immediately to this one, someone might erroneously put this right here as positive. So be careful. Okay. So minus minus is positive. And the sign is unchanged. This is a disgusting fraction within a fraction, so the easiest solution is just multiply top and bottom by 3. And that should be the answer for this problem. Let's do it the other way. Let's do this as a sine over cosine expansion. Again, if you forget this funky formula, if you forget this funky identity, then let's just do it as a ratio between sine and cosine. So sine on top, cosine on the bottom. There we go. And then, of course, this one right here, we have to do the proper expansion. This one we should do the proper expansion. Let's just do the easy way. So it's 3 pi over 12 plus 2 pi over 12, which will simplify into pi over 4 plus pi over 6. That's going to be term number 1 and term number 2 with a plus between those two. So sine will keep the same sign. But we have to mix up the trig functions. Sine, cosine, cosine, sine. Minus. For the cosine one, it's going to be plus on the bottom. But cosine, you keep the two types of trig functions together separately. Wait, that sounds weird. But keep the cosine with the cosine and keep the sine with the sine. So cosine first, and sine second. Alright, argument number 1 is, term number 1 is pi over 4. So pi over 4. Pi over 4. And same thing for the bottom one, pi over 4. Pi over 4. I'm kind of mixing up my order of operation, that's fine. And pi over 6 is for the second term. So I'm kind of going chaotically. Alright, we're referencing different reference angles than we did for this one, so we can't recycle this picture, which is fine, which is the whole intention, right? This is in quadrant 1, so that's easy. 1, 1, root 2, and this is quadrant 1 as well, also very nice. Alright, here we go. This is going to be root 2 over 2, standard. This is going to be that one, root 3 over 2, minus minus, cosine root 2 over 2, 1 over 2. Kind of cramped here. And you kind of copy paste stuff if you can find it very easily, right? Because we already evaluate that. We've already evaluated those. So if you can recycle your work, please recycle your work. If you want to. And lastly, 1 over 2. So it was looking kind of a mess. So we're going to have root 6 over 4. Same denominator. So I'm skipping a few steps. Same denominator. So 4 on the bottom, 4 on the bottom, so you could just clear that out by multiplying top and bottom by 4 if you wish to show full work. And then we get a familiar situation, right? Because we technically did something very similar to this one. So this is irrational denominator. But it ended up being like 2 and a root 3, right? Oh, I guess this was not simplified either. Okay, well, this one is going to be irrational for the denominator, and this is also irrational, so we need to change both of them. So again, just confirming that they are consistent, which you should probably rationalize depending on teacher, DOT. Multiplied by conjugate. What are we going to get after the conjugate? Alright, so that's going to be a 6 minus a 2, just speed running that one. And then this is going to be 6 plus 2, and then this one times 2. Alright, well, the bottom part becomes a 4. And then the top part becomes a 4 minus 2 root 12. This is simplifiable. It basically becomes 2 root 3. So this whole thing... What am I doing? This is 6 plus 2. So this is going to be an 8. I am very sloppy with this work. But that's what I get with the speed run. I would have lost the speed run. So again, the 6 plus the 2 gives us an 8. This one should become 4 root 3, thereby simplifying into 2 minus root 3. Is it equal? Well, conjugate. Conjugate. I'll try to speed run this one as well and be accurate. So we have a 9 minus a 3, and then top is going to be 9 plus 6 root 3 plus 3. Thereby simplifying into 12 plus 6 root 3 over 6, which is indeed this one, because 12 divided by 6 is 2. And then I probably botched the sign, didn't I? Yes, I did. Let me double check something. Oh my goodness. Alright, let's double check. Well, that's kind of frustrating, right? Okay, well, at the very least, we have 12 divided by 6 is 2, and then this one divided by 6 is going to be root 3. So at the moment, there's a discrepancy between the two signs. So one of these methods is wrong. And we love it when these methods end up seeming inconsistent. Well, I don't know which one's the wrong one. Okay, so I suppose that's nice that we're using independent strats. Well, slightly different, right? So they're not truly independent because ultimately they rest on the same properties. They just look slightly different. But at least we chose different breakdowns. And I'm just going to have to evaluate this one real quick to see where the error lies. Oh, let me think for a moment. I think that's what I get for speed running, right? Something botches up along the way. Okay, well, let's evaluate. Yeah. Yeah. And then... Yep. Yep. That is correct. And this one changes into that one. That should be correct. So everything should be positive on the top then. So that means this is likely wrong. Right? Yeah. So going back up here, what had possibly gone wrong? These are all in quadrant 1, so there are no sign changes. So this one stays as negative, yes. It stays as positive, yes. Yeah, so that should be correct. That should be correct. Yep. And yep. And then this one's a 6. Yes. 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 Okay, well, I'm not really seeing it, unfortunately. I don't know where the error has arisen. Where to proceed? Okay, so one of these is correct, right? It's either this one or it's that one. They both can't be correct because these are super simplified. So let me just redo it. So again, Voyage Watchers, you could just simply skip this part. The whole exercise was using a slightly different route. So this one is going to be evaluating this one as a ratio. We get this sort of situation, and this one may or may not be correct. Or you can use the more straightforward way if you've memorized it. The tangent expansion, you can get to this situation. But then these two answers look a little different, so I don't know where the error has occurred. Well, we don't need this one, and we don't need this one. So I worry that the original expansion is incorrect. You know what I mean? Okay, let's check this one out. Top and bottom times 3. Top and bottom times 2. This one does simplify into 5 pi over 12, which is what we're evaluating. Okay, so that should be good. Well, I'm just going to have to do it again. I have a feeling I bungled up something by speed running somewhere along the way, right? Alright, so let's check this out again. This is going to be a minus on top, so I'm going to not explicitly spell everything out. So it's tangent 5 pi over 4 with a minus sign still. Tangent 5 pi over 6 all over 1 opposite sign. Product of those two. Alright, making sure we hit the right reference angles. Oh no, we're not doing this one. This one. Oh, is that where things have been? Oh no, I'm doing this wrong. This is positive, so it's clockwise. Counterclockwise, so it's right here. Which I think that's what happened before, yeah. And this one is quadrant 2. Alright, evaluating that one hopefully correctly. Copy paste the signage first and then evaluate this one. That should be right. And then the bottom portion. Copy paste. Copy paste as well, and then this one evaluates into 1 plus. Evaluates into the minus. Yeah. Simplifying top and bottom times 3. There's an alternation of signs. And this one takes us back to this one, which multiplied by the conjugate. Yeah. Yeah. 9 minus 3 is indeed 6. 9 plus 12. 9 plus 3 is 12. Yep. And then this one should be correct. So I think I have confidence that this one is correct. This is probably the wrong one. Probably. Oh, that's a whole lot of to slug through again. Too bad. Again, you could always skip this if you're a VOD watcher. Let us clear the clutter. Huh. Okay. So using the other situation, we are evaluating for the 2 pi over 12 plus 3 pi over 12, which is essentially pi over 6 plus pi over 4. I probably mixed the order, but since this is summation, it doesn't really matter. Yeah, as long as we stay consistent. So this is going to be the cosine. I mean, sorry, sine over cosine. Pi over 6 plus pi over 4. You know what? Let me be a little more consistent. I like to put the larger one to the left. But it shouldn't matter. Alright, let's make sure this is correct. Yeah. That is indeed correct. And then doing the expansion, sine, cosine, cosine, sine. Plus, plus. Term number 1, term number 1, term number 2, term number 2. Cosine expansion, cosine, cosine, sine, sine. And term number 1, term number 1, term number 2, term number 2. Don't keep the same sign because this is cosine right there. Okay. Reference triangle number 1. Reference triangle number 2. And hopefully all goes according to plan. Alright, here we go. Yep. And then all over. Root 2 over 2, and then this one, that one. Okay. So the top part cleans up into root 6 plus root 2 all over 4. Pretty much the same thing on the bottom, but just as a subtraction between the top two. Clean up into 6 plus root 2 over root 6 plus minus root 2 conjugate. And here we go. Okay, good. The top part are all pluses. Okay, that looks good. I don't know what messed up before, but it looks like it's been fixed. Very interesting. Plus 2, I mean minus 2 plus 2 here, so that's 8. This is a 4. 2 times 2 is 4, so this becomes 2 plus root 3. Now it's consistent. What the heck? So this one is this. Wait, what? No. We got the plus. Yeah, we got the plus. We got the plus. This one is the wrong one. Yeah. I believe it's supposed to be plus. Yes. We've got 2 plus 3 from the second method, and we got the 2 plus the root 3 from the first method. So that should be correct. It's this one that was the weird one. Yeah. Okay. Yes. As a final check, I'm going to just punch in the calculator real quick, because at this point I feel like I'm mixing everything up. Alright, so let's see. What was it? We have tangent of 5 pi over 12. I just plugged it into my calculator, and the exact result is 2 plus root 3. Okay, so that confirms it. It's going to be this one, yes. So, according to the calculator, it's 2 plus root 3. So, that's consistent. So, the first one where I got 2 minus root 3, that was the one where things went wrong. Yeah, I don't know where that came from. I'm going to have to check the VOD afterwards. Okay. Well, that's it for this particular problem. Again, the answer was 2 plus root 3 for this problem. Alright, good to go. That was kind of a pain, but such is the nature of these problems. So, finishing up with the last 3 for this particular set. We have sine of 11 pi over 12. Alright, evaluating this one, we have the unfortunate denominator of 12, which is not our favorite, but we can split that. So we have a pi over 12 and b pi over 12. It's a plus or minus, but since it's close to 12, we could just put it as plus. It's probably easier for the plus. So how can we split the 11 into a and b, where a and b are simplifiable with 12? So basically a needs to contain some sort of factors of 2, 2, or 3, some sort of combo of that, and then b needs to contain factors of 2, 2, or 3, and or 3. And off the top of my head, 9 and 2 are the nicest ones. So a could be 9, because 9 is divisible by 3. And then b could be 2, because 2 is divisible by 2. And then 2 plus 9 is 11. So I think that is optimal breakup. So that becomes 9 pi over 12. And this one's 2 pi over 12. Summating those two, because 9 plus 2 gives us back to 11, yes. So that simplifies into 3 pi over 4. And that one's pi over 6. Alright. Looks good. So again, it was what was that? 3 pi over 4, and then pi over 6. Right? Yeah. We're good to go. This is simple evaluation. Sine, sine, cosine, cosine, sine. Term number 1. Term number 2. Sine keeps the same sign. And now just sketch out the reference triangles. This is 3/4 pi. So 3 is 1 short of 4, so we are in quadrant 2. The ratios are positive 1 to negative 1 to root 2. That one's just classic. 40, 30, 60, 90 in the quadrant 1 with the thin side 1 to 2 to root 3. Alright, getting the ratios, of course. We have this one, which is root 2 over 2. Root 3 over 2. It's always the same numbers, right? And then this one's going to be negative. So do the signage first, please. From the algorithm first, and then put the signage for the evaluation. Evaluate. Okay, so that should be safe at this point. So root 6 over 4, common denominator, plus minus is going to be minus, and then root 2. Should be correct for this particular problem. And then we're going to have 2 more for this problem set. And then we'll be free from the confines. Alright. Cosine. So that is the problem. How can we split up the 23? You don't have to write this stuff down. I'm just writing it just to show some work. We need to split up the 23. How do we split the 23? Into 2 terms. Each of those terms is divisible by somehow by one or more of these factors, right? I mean, you could just list this out if you wish. It could be, probably do a summation, because I think summation is typically the easier route to go. Probably. What makes up the 23, 15, and 8? Yeah, 15 and 8. 15 and 8. I like to put the larger one to the left. You don't have to do it like this. You could do 8 plus 15. It doesn't matter. 15, because 15 consists of 5 and 3, which is divisible by 3. And then the 8, which is divisible by 4, right there. So I think that's optimal. So we're going to split this one into 15 pi over 12. Which again, divisible top and bottom by 3, so we have 5 pi over 4. And then the second one is going to be 2 pi over 3. Alright. This is the cosine, so keep your trig function of the same types together. So cosine, cosine, sine, sine. That's a plus. This will be a minus. Term number 1. Term number 2. Sketch out the reference triangles. Not quadrant 2, this is quadrant 3, because we have the spillover. 5 is greater than 4 by 1, so it's the spillover into third quadrant. -1 to -1 to root 2 ratio. This one is in quadrant 2, because 2 is 1 short of 3, so we are stuck in quadrant 2. Opening up to the wider angle, because it's over 3. So root 3 to +2 to -1. So correct reference triangles, and now we just need to evaluate that one. Cosine is going to be -root 2 over 2. Parenthetical to keep things nice. Cosine of that one is -1/2. Copy paste. Evaluate individually. And what is that? -root 2 over 2? Parentheses. This one is positive. Alright, clean up. So the 2 negatives cancel out. 2 negatives cancel out. Same as before, or a previous situation. There we go. And that's evaluating this situation. At this point, it's probably getting tedious, right? That's okay. Let's do one more for the road. we got a tangent. 13 pi over 12. So I'm going to do this two ways again. I'm going to do the tangent way first, and then the sine over cosine root, the second method. And hopefully, this time, the answers will be consistent right off the bat. Same situation, we just got to consider how to break this up. So a pi and b pi. We need to split up that 13. 9 and 4, I think. Yeah, 9 and 4 is good. Because 9 is divisible by 12 to a certain extent. Or, I should say it's simplifiable, I'm sorry. Again, putting the 9 and then the 4. Because 9 is sharing a common factor with 12, and then 4 shares a common factor with 12. And those two sum up to be 13. So, I consider that optimal. So that simplifies into 9 into 3 pi over 4, and the second one is going to be pi over 3. Nice angles. So we have tangent. 3 pi over 4 plus pi over 3. Using the trig expansion root. It's plus on top. Plus. Minus on the bottom, and then it's a 1 minus the product of those two. You just have to memorize it, I'm sorry. Sketch out the reference. 3 is 1 short of 4, so we're in quadrant 2. Negative 1 to 1 to root 2 hypotenuse, and then that's 1, quadrant 1. 3 is on the bottom, so it's the wider angle. So root 3 opposite to 2 to 1 adjacent. Alright. Evaluation, of course. We have tangent. It's going to be negative 1. Copy the signage first. Then evaluate. Tangent is root 3 over 1. Which is just root 3. That feels different now. And we have a 1 minus. That one is that one. That one is that one. Cleanup step, of course. I'm going to switch the order of this. You know what? Let's leave the... I don't know. I guess it doesn't matter. I like to put the second. And that's going to be a plus. Alright, this is a rational denominator. There's a negative on top. Interesting, interesting. Okay. We need the conjugate to match the bottom because we want to create a difference of 2 squares for the bottom portion in order to rationalize it. Top one is a binomial expansion. So this one, 3 minus 1. Top one is going to be 3. This one times 2. And the negative 1 times negative 1 is positive 1. So therefore simplifies into 4. 3 plus 1 is 4. This one becomes 2. 4 divided by 2 is 2. And then negative 2 divided by 2 is negative 1 root 3 left over. So I hope this is the good answer. Let's do it the other way. Just for laziness sake, I'm going to keep the same split for the argument. So we're going to do sine, cosine. You know, no. Forget it. Let's not be lazy. Let's not be efficient. Let's be inefficient. So we're going to choose a different split. Rather than choosing 9 and 4, let's pick a different one. If possible. Can we pick a different one? Let me think. What splits 13, right? Let's just list them out. So we have 13 and 0, nope. 12 and 1, nope. We have 11 and 2, that's not good. 10 and 3, you know what? This one's good. Yeah, that's perfect. Because 10 is divisible by 12 to a certain like part of it is divisible, and then 3 and 12 is simplifiable. So let's do it like that. So we're going to do 10 pi over 12 plus 3 pi over 12. Yeah. So this one simplifies into 5 pi over 6. This one simplifies into pi over 4. So let's do that. So 5 pi over 6 plus pi over 4. So we're just trying to use different roots. Slightly different roots. Alright. Hopefully all goes according to plan. So we have sine, cosine, cosine, sine. Keep the same sign. Hopefully you get sick of this. Because if you get sick of it, that means you've memorized it. Hopefully. First term, first term. Oh, I even switched the order of that. Careless. Sine, cosine, cosine, sine. Oh, I broke up the answer. Hold up. So we're aiming for 2 minus root 3. So again, first term, and then first term. Second term. All over, and then we have this expansion for this one. Keep the cosines together. Cosine keeps the cos together, as well as the sines. But we don't keep the same sign. This is plus, so we make minus. Alright, we're just going to copy paste like that, because I'm following the same conventions. Reference triangle, this is 5 is 1 short of 6, so we are in quadrant 2 with the slim angle like that. This is going to be positive 1 to negative root 3 to positive 2. This is in quadrant 1. So everything's positive. Straightforward. Alright. And now for the evaluations, we have sine, which is 1 over 2. Which is root 2 over 2. Copy paste the plus. Let me get rid of this graphical glitch. There, it's gone. And cosine of 5 pi over 6 is going to be negative root 3 over 2. Parentheses. Sine of pi over 4. Alright. We should have the same values for the most part. So cosine of that is negative root 3 over 2. Cosine of that, root 2 over 2. Copy paste the signage. Evaluate individually. 1/2. Root 2 over 2. Just because it's so familiar. Alright, well, same situation. Root 2 over root 2 minus root 6 over 4. We have, what is that? What is this? Oh, it's a multiplication. Whoops. Multiplication. So that one is a negative. This one is also negative. Interesting. Alright, well, the 4s will clear from the top and bottom with that simple trick. And we're going to get root 2 minus root 6 over, very awkward, negative root 2 minus root 6. So we could factor a negative from the bottom and then slam dunk the negative and apply the negative to the top. So here's the trick. Factor out the negative from both terms on the bottom. So both signs flip. And we'll apply the negative to the top. And when we apply the negative to the top, the signs will alternate, thereby getting positive root 6 minus root 2. Rationalize that junk. It's looking good. I think we will succeed this time. Can we first try it? I hope so. Conjugate. With respect to the bottom. And here we go. We have 6 minus the 2 on the bottom, which is a 4. And then we have a 6. This one times 2 is minus 2 root 12. Signs cancel. Root 2 times root 2 is just 2. So this one is a familiar face, which becomes 4 root 3. So 6 plus 2 is 8. And we have a minus 4 root 3. 8 divided by 4 is 2, and then 4 divided by 4 is 1. So, hey, there we go, finally. So no discrepancies this time. Both methods, both breakdowns seem consistent. So thankfully we're good to go. Look at all that work. Alright, so I think that's what's actually going to conclude it for today. Next time, for the next stream, we're gonna be going backwards. So this is quote unquote going forwards. When we start off with a singular angle inside the argument, for the argument, and then we're manually splitting the inside into something plus something else, right? So if we consider that as going forwards, then this one is going backwards. So next time up, we're going to be working with problems like this, where you start off in the expanded form. So something like sine of pi over 12 times cosine 5 pi over 12. And then something like minus cosine pi over 12. And sine 5 pi over 12. So now we're starting off with this expanded situation, and then we're going to condense it to evaluate it. Because now the expanded form has the bad angles, so we're going to change that to condense it to make the nice angles. So going backwards, you know what, let's just do this one first real quick. So going backwards, this is a sine, cosine, cosine, sine. We know this is not a cosine, so when we condense this one, the algorithm doesn't condense into cosine, because again, cosines keep the cosines together. So this is going to be condensing into a sine situation. What are the two arguments? Well, since this argument perfectly matches this one, and this argument perfectly matches that one, I was going to say check. Just check to see what they add up to in the first place. So if we summate those two, we have 1 pi over 12 plus 6 plus 5 pi over 12. That summates to be 6 pi over 12, which is a nice interquadrant angle, which is perfect for us to evaluate. So that's how we can tell right away that it's going to be a good situation. So this is term number 1, this is term number 2. Before we even set it up, you should just try to see if they simplify to something nice in the first place. So here we have the term number 1 plus. Is it plus? No, it's minus, because sine keeps the same sign. This is going to be 5 pi over 12. Oh, that's interesting. Oh, that's okay. We still get a nice situation. So if you evaluate that, we're going to get the 1 minus 5, which is negative 4 pi over 12. This one does simplify into a nice scenario. We therefore get sine of negative pi over 3. So sketch out the reference. It's going to be clockwise with the wide angle opening up to the root 3. So it goes downward, so we have a negative root 3. So the ratio is negative root 3 to 1 to 2. So we have opposite is negative root 3, and then hypotenuse is 2. And that should be the answer for this particular situation. So that's the only one of this type that I'm going to go over today. The next time, for the next stream, it's just going to be many more of these type of problems. So I hope to see you there, and that's it for today. You have yourself a good one.